I'm Mike McBrien. This is SPH3U, Relative Velocity. Today our learning goals are to work out how to perform algebraic operations with vector quantities and use this to solve problems related to linear motion. So the concept that we're considering here is the idea of inertial frames of reference. We can blame Galileo and Einstein for these. The basic concept we're talking about is that we can add or subtract velocity vectors, as we've discussed previously. A really simple example: if an airplane's flying at 80 meters per second north relative to the air, but the air has a speed relative to the ground of 10 meters per second north, our airplane's velocity relative to the ground is actually the sum of those two. So 80 meters per second north plus 10 meters per second north gives us 90 meters per second north. In other words, the velocity of the plane relative to the ground is 90 meters per second north. We can also represent that operation algebraically. So in this case we can say the velocity of P with respect to A, the plane with respect to the air or relative to the air, and the velocity of the air relative to the ground. If we add those together, we get the velocity of the plane relative to the ground. So VPG equals VPA plus VAG. So what we wind up saying, what we have done in this case, is we have taken two objects with two different frames of reference and we related them to a single point of reference. And by doing this, we can compare their movement. We can do this simply algebraically because they both have what we call inertial frames of reference. And there's a really simple definition for this inertial frame of reference. It's any object or place that's traveling at a constant velocity. And of course, we know from our previous work that a velocity of 0 is still constant. All right, let's take a pretty simple example. These will get more complex as we go. So Anita rides a scooter at 4 meters per second north past B. And B is standing, okay, so we'll make it Brian. Brian, who's standing still. Anita's velocity relative to Brian is 4 meters per second north. But Brian has his own perspective on this. Anita has her own perspective on this. From her perspective, Brian's velocity is 4 meters per second south. And both of their perspectives are equally valid. Okay, another case. Charlie rides a scooter at 1 meter per second south past Brian, and Brian's still standing still. Charlie's velocity relative to Brian is what? Well, we can say his velocity relative to Brian is 1 meter per second north, of course. And again, we can reverse this and say Brian's velocity relative to Charlie is 1 meter per second north. Our second example, we're going to combine those two things. So Anita's riding her scooter again at 4 meters per second north toward Charlie, but Charlie's moving at 1 meter per second south Now what are their relative velocities when we compare Anita to Charlie? Remember, both of them are moving. And we can go to our vector addition case again. And what we can do is we can say that, again, we treat these almost like, well, not almost, we treat these like line segments. So, AB, if we look down at our equation down here, AC equals AB plus BC. And this is, of course, the velocity of Anita with respect to Brian, the velocity of Brian with respect to Charlie, and then we can get the two things that weren't mentioned in our problem, the velocity of Anita with respect to Charlie. And if we go through the math here, we get that Anita's movement with respect to Charlie is 5 meters per second north. So I refer to B as Brian, but since Brian's standing still, this is, I guess, the most common case we'll tend to talk about. With Brian standing still, effectively, he's the Earth. So we could have just as easily taken Brian's position as being the Earth itself, which is very often in these problems taken as a point of reference and used as a useful point of reference, but not always. Okay, and so that problem, Anita's velocity relative to Charlie is 5 meters per second north. Charlie's velocity relative to Anita, of course, is just the negative of this, the opposite direction, so 5 meters per second south. Now, example 3 is a tiny bit different because Anita and Daryl are both moving in the same direction, right? So Anita's velocity is 4 meters per second north, and it implied with respect to the ground. And Daryl's velocity is 1 meter per second north. So hopefully it should be obvious to you what you need to do in order to figure out their velocity with respect to each other. But we can make it explicit again. We introduce again Brian, or the ground, we can take our pick on that, and get the velocity relative to B of Anita with respect to Brian, get the velocity of Brian with respect to Daryl, and then we can get the velocity of Anita with respect to Daryl. Something worth noting here is that when we go down to our our vector case, our algebraic case, we can see that we have reversed the direction. In order to do addition, we wind up reversing the direction. And this is because we had our velocity of D with respect to B. But you'll notice that in the case up above, we have the velocity of B with respect to D. So we reverse the sign, made this south, and we subtract to get 3 meters per second north as our relative velocity of Anita with respect to Daryl. And of course, Daryl's velocity with respect to, or relative to Anita, is 3 meters per second in the opposite direction, or 3 meters per second south. So those questions are relatively simple and just take a little while for us to get our heads around. However, we can be given much more complicated problems and use the exact same fundamental concepts to get the answer. So this a little bit silly problem can illustrate this very well. If we have a boat traveling at 6 meters per second north, relative to the river, which is flowing at 2 meters per second south, and a monkey on the boat walking along the boat at 2 meters per second north, relative to the boat, and then he throws a banana behind him at 3 meters per second relative to himself, we have a really interesting problem. And then we can complicate it further by having a bird flying over the boat with a velocity of 1 meters per second south. And Selma's back, and she's standing on the riverbank, watching all of this occur. We can use all of these concepts to find the velocity of the observer relative to the monkey, the bird relative to the monkey, and the banana relative to the bird. And all we have to do is apply these concepts effectively. So we already understood the concept of reversing the sign in order to find the relative velocity. Remember, we were given the velocity of the observer with respect to the monkey. To get the monkey with respect to the observer, we reverse the sign. And we get that the monkey, from Selma's point of view, is moving 6 meters per second south. But the bird has a velocity with respect to the observer of 1 meters per second south. The velocity of the bird with respect to the monkey, then, is the sum of these two things, or 7 meters per second south. And then if we want to get the banana relative to the bird, we can take the banana with respect to the observer plus the observer with respect to the bird and get 4 meters per second north. It may take you a few minutes to get your head around this, but really it's simple algebra once you think about it. So why is it worthwhile to think about these things in this way? Well, we can solve, as soon as we've established how to do this, we can solve some problems that would be quite complicated without this concept. For example, a football player running 4 meters per second north toward a second football player running 3 meters per second south. If they're 25 meters apart when they start, how long before they collide? Very challenging to do this problem if we don't combine their velocities by changing the point of reference from the ground, which is how we started, to one of the other perspectives, either the perspective of the player A or player B. Similarly, we can take the problem. Actually, well, let's talk about that for a second. So, rather than considering the two objects, we determined that the velocity of B with respect to A is 7 meters per second. Once we know this, it's a trivial problem to find out how long it takes to cover that 25 meters. Okay, a second example, and very practical, is the idea of flying an airplane. And I alluded to this in class earlier. Let's say we have 2.3 hours of fuel left, and we know that our cruising velocity is 226 kilometers per hour north. Now, what's that relative to? Well, an airplane, the only reference that really matters to an airplane is the air. So what if we have a headwind of 28 kilometers per hour south? Well, we need to be able to consider that problem very accurately to make sure that we can reach the airfield 500 kilometers away. Using the tools we just learned, we can figure out if we've got enough fuel. Okay, so those are the basics. Now let's open up the homework and start to work through some of the problems that are available there. We'll discuss them in class.